Welcome back to your physics buddy. Today marks a major milestone. This is officially the 90th lecture on this channel. Over nearly 100 sessions, we have built a library specifically engineered for AP Physics 2 curriculum, ensuring that every student appearing for the exam has a high yield resource they can trust. We are now entering the Unit 12, Magnetism and Electromagnetism. This unit is all about visualization. We are moving from 2D circuit diagrams into a 3D reality of invisible fields. If you want to master the AP exam, you need to see the physics, and that is exactly what we are doing today. Here is the roadmap. In this first lecture, we'll master magnetic fields and forces. Next, in lecture 2, we'll scale up with rigorous problems from the Wilson and Buffa framework. Finally, in lecture 3, we'll apply it to all Earth's magnetism and transformers. Whether you have watched all 97 previous videos or you're just joining this course, this course is designed to get you results. Grab your notebook, focus on the screen, let's dive into the magnetism.
So this is 12th unit, magnetism and charged particles. So it's a very basic and fundamental thing. When we talk about magnets, so for magnets, end poles basically they are called south and north. If there is the same pole, like one, it is going to repel. If it is an opposite one, it is going to attract. So this is something which you already know. Apart from this, the most important thing about magnets is if you try to cut the magnet into two halves. So eventually, if you try to break the magnet in such a way that south and north pole can be put apart, but it is not the case. Magnet will automatically generate the opposite pole, which is the missing one if you break it even. Apart from this, magnetic field, something which can be visualized using this simple diagram. So if you just place iron fillings near the bar magnet, the iron fillings will acquire this kind of structure. So this is something which we call magnetic field lines. So the most important part here is that magnetic field lines are always closed loops. Like for if you talk about electric field, we know that it started from positive charge and end, or you can say terminate at negative charge. But this is not same with the magnetic field. Magnetic field will form a closed loop. So if something is going away from the north pole, or you can say coming out from the north pole, it will terminate into south. But inside the bar magnet, field will be from south to north. So this is how they form closed loops. Similarly, uniform magnetic field, if you talk about, so it is constant in magnitude and direction when it is near the poles. So if you're talking about two white poles which are nearly uniform, then field is going to be uniform as well as constant in magnitude and direction. The most important relation here, force, which, or you can say the magnetic force which is exerted by a charged particle in motion. When we began this course, we just understood that why there are different kind of fields. If charged particle is at rest, it produces electric field. If charged particle is in motion, it will produce magnetic field. So that magnetic force is something which is QVB, where V and B is the cross thing. So it is V cross B, or you can also write it as QVB sine theta. So this is one such relation that you need to remember. If you have to find out the direction of force is given by right hand rule. In right hand rule, or you can say direction of force is given by the direction of cross product, that is V cross B. Whatever direction this cross product has, that is the direction of magnetic force acting between the poles. So this is a conceptual question. The question says there is a negative charge minus q which is placed at rest near a magnet. Will the charge begin to move or will it feel a force? What if the charge particle was positive? So the question is simple, like if there is a bar magnet and close to the bar magnet we just kept a charge. It can be positive or it can be negative. So we have to actually answer this thing that whether it is going to act as whether the force is going to act on it. What do you think?
Uh, it will be repulsive.
No, the question is, will the charged particle move?
Yeah.
Mm, the answer is yes. You said it right. It depends upon the magnetic field. Whatever magnetic field this bar magnet is possessing, under the influence of that magnetic field, this charged particle might move. So whether it is positive, whether it is negative, it will move, but the direction of motion will be different. So that is what we need to keep in mind. There is another example in which there is a force which is acting. There is a magnetic force which is acting on a proton. So we just have to understand the motion. So the question says that magnetic field exert a force of 8 into 10 to the power minus 14 newtons towards west. So there is a charged particle which is positive. It is experiencing a force in west direction. And upon this, the proton moving vertically upward at a speed of 5 times 10 to the power 6 meters per second. So because of this, this charged particle is moving upward. Force is acting across west side, but the charged particle is moving upward. So the question is determine the magnitude and direction of magnetic field in the region. So what is the magnitude and what as well as what is the direction of magnetic field? So what we have to understand here is we just have to curl the fingers of our right hand from V to F, like direction of velocity to direction of force, and the thumb which is pointing outward out of the plane, it is going to give us the direction of magnetic field. So this is what you have to do here. So the magnetic field must be acting out of the plane like that. So this must be the case how magnetic field is acting. And if we have to find out the magnitude, so we can say magnetic force must be equals to QVB, and Q is something which is proton. So proton has charge of 1.6 times 10 to the power minus 19. Similarly, if we have to talk about the velocity, it is 5 times 10 to the power 6. Apart from this, the magnetic field is 8 times 10 to the power minus 40. Once we solve this equation, we'll have the force. So this is what we are supposed to find out in this question. Similarly, if there is a charged particle that is moving in a vertical circle, or you can say in a circular motion, so we have to understand this that one, there is a magnetic force which is acting inward against it. There must be a some force which is called mv square by r, which is centripetal force, which must be acting outward. So because of these two forces, the path becomes circular, or you can say the force which is acting inward must be equals to mv square by r. The force which is acting inward, it must be qvb, where v is the velocity, b is the magnetic field. It must be equals to mv square over r. We can cancel out velocity and velocity, and if you have to find velocity, we can find it out as qbr over m. So this is the relation for velocity that we might use in some of the questions. Apart from this, we can also find out radius from this. So there is a conceptual question. Question says, can a magnetic field be used to stop a single charge particle in an electric field as an electric field can? So question is, can magnetic field do the same just like electric field do, like stopping the single charge particle? It can. So this is something you have to remember. Now there are certain problems which is related to your you can say direction thing. Magnetic force is perpendicular to the magnetic field direction. We have to remember this. The right hand rule is useful for determining direction. Questions in this chapter give the magnitudes only. The right hand rule gives the direction. These are the 3 points that you need to keep in your mind while solving problem. Apart from this, if magnetic field and the direction of motion is something which is not 90-degree, like for example, we talked about force is QVB, where V and B must share cross product. So it can also be written as QVB sine theta. So this magnetic field is basically, this theta is basically the angle between velocity and magnetic field. Now what we have to understand here is that if the angle is not 90-degree, then what? Then the path is going to be helical. This is how the path of the charged particle looks like. So this is the difference that you need to remember. If it is 90-degree, if angle is 90-degree, that is like velocity and magnetic field are perpendicular. It would be a straight line. But if it is angle is something less than 90-degree, it is going to be helical. Whereas if forces are properly balanced, it must go in a circular path. So these are the conditions that you need to remember. So electron were first discovered in cathode ray tube. We already know this thing. These tube had very small amount of gas inside, and when high voltage was supplied to the cathode, some cathode rays appeared to travel from cathode to anode. This shows that there is a proton which is traveling. Similarly, you have to keep in mind this ratio as well. Charge by mass ratio for cathode ray was 1897. That is something you need to remember. We don't go to the experiment part, but this is something that you need to remember. Similarly, Millikan measures the electron charge directly shortly thereafter using oil drop apparatus. So he does the same, and because of this, we were able to find out mass of electron as well as charge of electron. Then there is one effect called Hall effect, which generally explains that how charged particle is going to move inside magnetic field region as well as electric field region. So we don't need to go deep into it. Mass spectroscopy, another branch of physics which deals with magnetic field and electric field. So I don't think so we need to go deep into it, but yes, the relation which we saw for the circular motion, that is something which we use here. So always remember QVB must be equals to mv square by r. If particle is in circular motion, these are the forces which must be equal. And remember this relation and you're good to go. Let's move to the next topic. That is 2.2 magnetic forces on current carrying wire. So if there is a wire which is carrying some current, so that wire is capable of producing magnetic field around it. And how we can find out the magnetic field? Again by using right hand rule. What you have to do here, you just have to put your thumb in the direction of current, just like this. In whatever sense your fingers of right hand is getting curled, that is going to the direction of magnetic field, just like this. So these are forming a circular loops, circular concentric loops, considering the circus, considering the line or the wire to be at the center. So this is how you can find out direction of magnetic field. Similarly, we need to understand this thing that there is electric current which flows in the circuit that can actually causing magnetic field. So if there is a magnetic field, it can simultaneously produce electric field. If there is magnetic electric field, it can produce magnetic field. So this is what the concept of EMW, electromagnetic waves. So if you define force, we can define out using current as well. If there is a current, it will capable of producing magnetic field. If it is capable of producing magnetic field, it can actually apply force on charged particle. So this is the reason why when we are having wires carrying current in our home, they are crisscross. They are, like you can say, entangled in one to other. This is because the wire can apply actually force on another wire. So in order to avoid that repulsion, we just crisscross that wire. Although the wires which we are using at home, they are not thick in area, or you can say greater in radius. So that is the reason why we can use them directly. Similarly, if we are calculating force, so there is another relation which we are using to calculate magnetic force due to current carrying wire, which is IBL sine theta, where this I is going to be the current, L is going to be the length of the conductor, and B is going to be the magnetic field. So these are the formulas that you need to keep in your mind to solve problem. Again, remember, we are using before equation for charge particle. Now we are talking about current carrying wires, and this is the force formula which we'll use to calculate field, or you can say force due to current carrying wire. And this is the angle, and that angle is between length and magnetic field, basically conductor and magnetic field. So in whichever way the conductor is kept according to with the magnetic field, that angle is going to something which we'll use here. So this equation defines magnetic field. You already understood this, I guess. It's important to remember that unit. Magnetic field has Tesla. Another unit is Gauss, which is 10 to the power minus 4 Teslas. Now this is an important relation. We'll be using this relation in so many numericals. So what this relation says, so if there is a current carrying wire and there is a point, this point is at certain distance, let's say R. So if we have to find out magnetic field at this point, so the magnitude of magnetic field is calculated by mu naught I over 2 pi r, where mu naught is 4 pi times 10 to the power minus 7 Tesla meter per ampere. This is important. This is the formula for magnetic field due to a current carrying wire in any plane. So this is that plane in which we are calculating magnetic field. At any point, we just have to understand what is the value of current, what is the radius, like what is the distance from the current carrying wire. That's all. That is your you are going to use. So the same formula you'll apply here, you'll get the answer. Current must be given here, that is 25 amperes. So we'll substitute the values into that relation and we'll get the answer. So we'll discuss it through the homework problem. Apart from this, again, this is going to be the same one. We'll calculate the magnetic field B1, we'll calculate the magnetic field B2, and ultimately we'll have force, whichever we needed. We can simply use the relation which we saw in the last page. Let's do this one. So this is the magnetic field due to 4 wires. If there are 4 wires and we have to find magnetic field, how we can say this? So the question says the figure shows 4 long parallel wires which carries equal current into or out of the page. So cross means into the page. So wire must be going into the screen, and out means, and dot means out of the page. So you can imagine that there is a wire which is like that, and they are carrying current, and all these wire carrying current in different direction. One is taking into the plane, another two is taking out of the plane. So because of these wire, if we try to find out the magnetic field, so the question is in which configuration, A or B, the magnetic field greater at the center of the square. In which direction it is going to be greater, in first or in second? So its answer lies within it thing only. Like how you can say this, if there are forces acting opposite to each other, like in this case, so this field will cancel out this field. Similarly, first field due to first wire will cancel out field due to fourth wire. This will also cancel out. So in the second case, we can say net magnetic field at center is going to be 0. And whereas in first case, net magnetic field will be towards left. So we can clearly see in configuration A, field is more at center in comparison to configuration B. These kind of questions will be there. Another important relation, we already know magnetic field due to one wire at a point, it is mu naught upon 2 pi I by R. So here I is written as I1 and R is written as G, because we are talking about two wires, two parallel current carrying wires. So the force relation changes here a little. We will simply say it is going to be mu naught upon 2 pi I1 I2, whatever current these two wires are carrying. Length, what is the length of the wire over distance between them? So this is what you need to remember. Length of the conductor is L2. Again, these are the formulas which we'll be using to solve problems, homework problems basically. This is going to be length, this is going to be distance between wire. So you have to identify in the question itself that what is given here. I1, I2 will be the current. This is going to be the force. Similarly, if the two wires carrying current in same direction, the force is going to be attractive. Whereas if the wires are carrying current in the opposite direction, force is going to be repulsive. That is what we need to remember here. Another question is there, we'll use the same thing. Now this is the definition of 1 ampere which we got from the relation which we found in a slide. So it is mu naught upon 2 pi I1 I2 over D into L. So from this relation only we define 1 ampere, the value of 1 ampere. So 1 ampere is defined as the current flowing in each of the two long parallel wires which are 1 meter apart, result in a force of 2 into 10 to the power minus 7 newtons per meter of length of each wire. So from this statement only we got this definition of 1 ampere. Try to remember the relation for torque we learn in electrostatics, which is P cross E. Here it's a little difficult, a little different. It is M cross B. In magnetism, the torque relation becomes M cross B, where this M is the product of current into area. For number of loop, it is going to be NIA B sine theta. So that is something you need to remember. Torque in magnetism is M cross B, whereas torque in electrostatic is P cross E. So similar relations, this is what the analogy we have between the electrostatics and magnetism as well. There is one such application. We have galvanometer here, which measures the current, which is used to measure a very small magnitude of current, which emitter can't measure. So that is the difference between emitter and galvanometer as well. You need to know. Now let's just move to the next section of this unit, which is again electromagnetism and magnetic material. So here we are going to talk about magnetic field due to different configuration. One is solenoid, another is toroid. So this is the relation which you need to remember. Magnetic field due to solenoid or toroid is nothing but mu naught Ni, where this N is the number of turns per unit length. What does this means? Number of turns per unit length. It means whatever length of solenoid we have, the small value of N is equals to whatever number of turns it possesses, whatever length it has. So number of turns is going to be represented by capital N, which is equals to small n by L. Or here you can say the small n must be equals to capital N times L. So this is how we are supposed to find out number of turns. So that is something you need to remember. Similar question, you just have to put the values in the relation. That's all. So these are the applications of magnetism, mainly solenoid and toroid. Apart from this, we have electromagnet as well, which uses the same concept. First magnetic material we have is ferromagnetic materials, which are very strongly magnetized, like iron and nickel. They have like all the dipoles in the same direction, which creates a stronger magnetic field. So that is something you need to remember. If the magnet is unmagnetized, the domains are randomly oriented. But when they are put into the magnetic field, they are completely arranged in a fixed direction. That what makes it different. A magnet is undistributed while tend to retain its magnetism. It can be demagnetized by shock or heat. So this is how we can make a non-magnetic material a magnetic material. This is an important table for diamagnetic and paramagnetic material. Now just try to remember the order which I am saying. Paramagnetic material are those materials which are strongly magnetized. Diamagnetic, little lesser than that, and paramagnetic, almost nothing. Hard to magnetize them. So that is the thing we need to remember. Who is more magnetizing capabilities having and who is not. That is what you need to remember. Then we have paramagnetism and diamagnetism. That is the same. Geomagnetism is also one such thing which is representing the magnetic field or field patterns of Earth. So that is also you can remember. So now let us just move to the questions and let us try to answer a few of them. So this is the first question we want to discuss. That is question 2. The question says that there are two identical bar magnets of negligible width located in XY plane. So there are two bar magnets which are located in XY plane. XY plane is what? Suppose if this is a plane, so this is going to be the XY plane, the horizontal one, where this line, it is actually representing vertical plane, that is Z. So question says first the magnetic one lies on x-axis and its north located at x is equals to plus 1 centimeter and its south is located at 5 centimeters. So this is going to be the bar magnet. This is the position of bar magnet on x-axis. Whereas magnet 2 lies on y-axis, its north end is plus 1 while its south end is plus 5. So another bar magnet is kept like that on y-axis. In what direction would the compass point if we were locked at the origin? So if we were standing here, or the bar magnet is placed such way, and we are calculating the magnetic field at this point, how it is going to show the magnetic field lines? That is what we have to answer. So question says the position of north and south pole. That is what we have to understand. North end is plus 1, so this is the north end. This is south end. Similarly, north end at plus 1 y as well. So north end, south end. So magnetic field must be going out like that. So at this point, magnetic field direction must be this way. That is between positive x-axis, between negative x and negative y. So magnetic field will lie between negative x and negative y. That is what we need to remember. Repeat part A for the situation where magnet is reversed in polarity. Make a sketch of the two magnets and their individual field at the origin. So this is how you're supposed to do. One magnet field line must go like that. Another magnet drawn that way only, but in different plane. The field must be going like that here as well. So ultimately you will be observing the field will be that way for both the magnets. So it will lie in between them. That is how you're supposed to answer this. So you just have to find out the field, you just have to find out the magnet's position to identify different things here. So question number 3 is almost similar to that one. You can try it out later on as well. If we move to the next question. The question says, let us try to understand it. A positive charge moves horizontally to the right across this page. So we can imagine that this is the positive charge and it is moving towards right like that. Enters a magnetic field directed vertically upward, vertically downward. So there is this magnetic field. It is directed vertically downward like that. The question is, what is the direction and direction of magnetic force on the charge? So what is the direction of magnetic force? So you can say this is the velocity of the direction. This is the direction of velocity of charge particle. This is the direction of velocity magnetic field. So as we already know that magnetic field is getting downward, velocity is in forward direction. So magnetic force must be perpendicular to both of them, like this way. How we found this? Using right hand thumb rule. If velocity in positive x-axis, magnetic field is negative y-axis, so force must be acting in positive z-axis. That is what we need to understand here. Second question is, magnetic field is out of the page. If magnetic field is out of the page, it means velocity is this way, but magnetic field is this way. So in which direction force is acting? Now force will be acting in the downward direction. Direction of force will change. If field is again positive, velocity is again in positive x-axis, field is in positive z-axis. So force will automatically become in positive y-axis. This is how it will change. So always remember all these things. These are the these are the three dimensions, and only in these three dimensions we are supposed to write the answer. So always remember, first of all, figure out which two directions is being used, velocity and velocity and magnetic field. Whatever the third dimension remains, that is going to be the answer. Now, let us try to answer this B part. If the charge is 0.25 coulombs, its speed is 2 into 10 to the power 2 meters per second, acted upon by a force of 20 newtons. What is the magnetic field strength? Now, it is pretty simple. Force is what? QVB. We have to find out magnetic field. Force is given as 20 newtons. Charge particle is 0.25 and velocity is 200. 200 is given. So, what you can do? It is simply 1 by 10. It is going to be 2.5. We'll write it this way. It is going to be 0.4 Tesla. This is what the answer is going to be. Did you got this?
Yeah, kind of.
Yeah, it's pretty simple. Just try to understand it. You just have to
Okay.
use the formula and plug all the variables given in the question.
Okay. Okay.
But you need to be focused with this thing, that how you're going to assume that which is what. Charge is 0.25. Coulomb is the unit. So you can easily identify using Coulomb, capital C.
Okay.
Speed is meters per second. Force is always Newton. So you can easily guess all those things. In the follow-up question, question number 5, charge is 0.05 coulombs. It is moving up vertically upward because of the field of 0.08 Tesla. That is oriented 45 degree with the vertical. Now, this is the case in which I told you that force is QVB sine theta. So we are going to use this formula here, this relation here, to answer the question. What speed must the charge have such that the force acting on it is 10 Newton? So we have to find out the velocity from this equation by simply using this relation, that is force is QVB sine theta. So for velocity is going to be force upon QB sine theta. We have given everything here. Force is 5 newtons. Charge is 0.25. Sorry, 0.05. Can you plug all the values in the equation and tell me the answer? You just have to solve this equation and you'll have your answer.
One
In
to
fifth,
50.
in fifth question, force is 10 newtons, not 5.
Okay.
In sixth, it's 5.
Thir 35, 35.5. That's what I'm getting as answer.
Yeah, you can get that. No issues in that. So question number fourth was done. Question number fifth is done. Similarly, question sixth is the similar one. Completely same question, no changes. You just have to substitute the values into the relation, assuming angle is there. Because in that case, we have to actually find the angle only. So you can just put your all the necessary thing into the equation and you'll have the angle. Just put sine theta into the one side of the equality and all the other variables into the other side. Substitute the values, you'll get the values for sine theta is equals to something. So you can easily find out the theta using calculator once again. So that is again you can use and solve directly. In question number 7, it says that a beam of proton is accelerated to a speed of I guess 5 times 10 to the power minus 5 times 10 to the power 6 meters per second in a particle accelerator. So particle accelerator is basically a device we can use to accelerate large particles and emerges horizontally from the accelerator into the uniform magnetic field. So the question is, what magnetic field oriented perpendicularly to the velocity of the proton would cancel the force of gravity, keep the beam moving exactly horizontal? So this is a tricky question. So let us try to understand what exactly is taking place here. So question says that the protons which are accelerated by this particle accelerator is moving horizontally. They are going horizontally like that. But this charged particle do feel some force acting downward, which is due to their gravity, which is mg always. This is the velocity of the charged particle which is coming out, and that charged particle is nothing but proton. So why they are not falling downward? That is what the question. Because there must be some force which is acting in the upward direction, which is going to be the magnetic force. And that magnetic force is simply represented by Fb. And what this magnetic force equals to? It is equals to QVB sine theta. So this is what this is being asked in the question. What is the force keeping that thing vertically exactly horizontal? So mg must be balanced by this magnetic force, which is QVB sine theta. That's why it is not heading downward or going downward. Did you got this one? Did you understand the seventh one?
Yes.
Similarly, eighth question is kind of same. You have to identify the magnetic field using the relation QVB sine theta once again, or in the direction as well. Again, remember right hand thumb rule. In question number ninth, again same question. Nothing is changed. You just have to identify the magnitude of magnetic force, that is QVB, keeping different things in mind. When they are perpendicular, so sine theta is going to be sine 90. When it is making angle 45, so sine theta must be sine 45. Are parallel. Parallel means theta is going to be 0. So when theta is 0, force is automatically 0 because no force will act if velocity and magnetic field are parallel to each other. And exactly opposite. Exactly opposite means sine 180. And sine 180 is also 0. So in that case also force is going to be 0. So very basic question. Just you have to rely on the formula. Then after this, we were supposed to answer question number 12. Let's move to question number 12. So 12th question says that there is an ionized deuteron, a bound proton neutron system with a net positive E charge passes through a velocity selector. Electric field has magnitude 40. Magnetic field has magnitude 40 millitesla, whereas electric field is 8 kilovolt per meter respectively. Find out the speed. Now let me just give you a very simple answer here. When QE is equals to QVB, what does it mean? It simply means when electric force is equals to magnetic force, velocity is equals to electric field upon magnetic field. So once you divide electric field with magnetic field, you'll get your answer. What is the speed of the ion? Electric field is what? 8 kilovolt per meter. So 8 kilovolt means 8 times 10 to the power 3 volt per meter. Whereas magnetic field is 40 millitesla. So it is going to be 40 millitesla means 10 to the power minus 3. So this is going to be 1 by 5. 1 by 5 is 0.2. So it is going to be 2 into 10 to the power 5 meters per second. This is what you have to do. This is how simple it was. But again, you can only do this if you know the relation. What is the relation? Electric force equals to magnetic force. And that is the case of velocity selector, which we use to give the velocity to a given charge particle. This is how we're supposed to solve this. Apart from this, you have to answer 13th as well. So this is again a simple question of velocity selector. Always remember the relation. Electric force must be equals to magnetic force. If it is equal, you can use all the conditions, and this is something which is applied in velocity selector. What is electric force? Electric force is Q times field, electric field, and magnetic force is something which is Q times velocity times magnetic field. That's all. You can apply this relation and find out and ask me to do, and you can already do this on your own. A pretty simple thing. Apply the same formula for velocity as well as for the remaining questions till question number 14th. Similarly, another one is also pretty simple. The question says, in an experimental technique of treating deep tumors, unstable positively charged p ion, which is pi ion, you can also call it, elementary particle with mass of 2.25 times 10 to the power minus 28 kg. It penetrates the flesh, disintegrates the tumor site, releasing energy to kill cancer cell. So we are using this charged particle, which is called pi ion. So this pi ion with kinetic energy, 10 kilo electron volts are required. So this is the kinetic energy. Always remember, kinetic energy is also equals to charge times potential. This is what kinetic energy is also equals to. Are required if velocity selector of an electric field strength 2 into 10 to the power 3 volt per meter is used. We have given the electric field strength here, which is what? Which is 2 times 10 to the power 3. Question is, what is B? What is magnetic field? How we are supposed to answer this magnetic field in this case? So one thing is pretty sure, magnetic field can be found out using velocity selector principle. And velocity selector principle, magnetic field is electric field per unit magnetic field. This is what velocity is. So magnetic field strength is going to be electric field per unit velocity. How can we find out velocity? We can find out velocity using kinetic energy thing. Kinetic energy is also equals to half mv square. So if you use the value of half mv square, so kinetic energy is also equals to half mv square. From here you can find out value of velocity. Kinetic energy is already given, 10 kilo electron volts. What is kilo electron volts? 1 electron volt is 1.6 times 10 to the power minus 19 joules. Again, this is a relation you have to keep in mind. So 10 electron volt is going to be 1.6 into 10 to the power minus 18 joules. You got the value of kinetic energy. You have the mass here, 2.25 times 10 to the power minus 28 kg. You substitute the values in this relation, you'll get the value of velocity. Whatever value you'll get for velocity, just divide that value by E. You are getting magnetic field afterwards. So not a difficult one, but yeah, if your basics were clear, you can easily answer these type of questions as well. Did you got this one?
Yeah.
I hope you are writing everything along with me.
Yes.
Otherwise, when you try it on your own, you won't be able to remember all these. And make sure you solve them as well. Whatever I am letting you know, you write all the relations, all the formulas which you are going to use, and make sure you solve them. Because once you solve this, you'll get the answers, you'll get confidence automatically. And that is what you have to work upon. Alright, so afterwards, so that is all you can do from that particular topic, I guess. Let's move to the next topic, which is magnetic force on current carrying wires. So from this page, you mentioned question number 20 to 27. So let's move to question number 20. Alright, so question number 20 is again pretty simple. Again, I told you to remember the relations, important relations which we understood from the PPTs as well. Magnetic field due to a current carrying conductor is equals to mu naught over 2 pi I by R. Now this is the relation which we are going to use here. The question says a straight horizontal segment of wire carries a current in a x-axis. So there is a current going in x-axis because the wire is placed in that direction. Magnetic field is that is directed in negative z direction. So current is going in this direction, I is going in this direction. Magnetic field, it says it is set up in positive negative z direction, means like that. Is the magnetic force on the wire directed in negative x, positive z, positive y? So you have the direction of current, you have the direction of field. What should be the direction of magnetic force? That is what is asking. We understood one more formula for force, which is IBL sine theta. We'll be using this relation to actually understand what is the direction of magnetic force here. What do you think? What it should be? If it is negative z, if it is positive x, the direction of force must be positive y. They should be mutually perpendicular to each other. That is what you have to remember. That's all.
Okay.
Nothing else is need to be remembered. If it is upward, if it is positive z, field is going to be negative y. Force is going to be negative y. If magnetic field is positive z, field is going to be negative y. That's all. Whichever third direction you found, just consider that as your answer. In most of the cases. Not in all, but yeah, in 90% of the cases, answer is going to be that.
Okay.
Similarly, in B part, it says if the wire is 1 meter long and carries a current of 5 amperes. So we have given length L, we have given value of current I, we have given magnitude of magnetic field P. What is the magnitude of the force on the wire? You just have to put IBL. You put the values in this relation, you'll get the answer. That's all you have to do. You can easily try this on your own. Question number 21. Again, you have to apply this relation IBL sine theta. Here the value of sine theta is given as 37 degrees Celsius, 37 degrees. You have given the value of length 2 meters. You have given the value of P, magnetic field 50 millitesla. You have given the angle as 37 degrees Celsius. Apart from this, you have also given the value of current as 20 ampere. You substitute the values in this relation, you get the value of force. That's all you have to do. Similarly, question number 22 is going to be the same. Force we have to find out the force. We have given the value of current, we have given the value of magnetic field, we have given the value of length. We have also given the value of theta, that is sine 30. We have to substitute. Substitute all the values, you'll get the value, you'll get the answer. You'll get the answer for the force. If the question is reduced to half, if the angle between the wire, what should be the angle between the wire required if we want to reduce the value to be half? So you just have to put the value f as f by 2, whatever value you are getting. Keeping all the things same, you can find out sine theta by substituting the reciprocal values. That's all. Now again, the whole question, number of questions that you have seen till now, these questions are based on formula. If you know the formula, you can substitute it, you can solve it. If you don't know the formula, you won't be able to do it. That's all. That is what you have to keep in mind. Question number 23 is also the same, but here you have to find force per unit length. Now what does it mean? What is the difference between force per unit length and force we are finding in the questions above? So force is IBL sine theta. So force per unit length is going to be force upon length I times B. So that is what you have to apply here. Force per unit length means you have to simply multiply current and magnetic field. Once you multiply it, you will get it force per unit length. So that is also pretty simple, but the way question was asked is different. Otherwise, everything is same. Similarly, if you look at some other problems as well, these are also going to be the same one. Now in question 24 as well, you have to find out magnitude of magnetic field is given, length of wire is given, along which axis would the current direction has to be to cause the direction subject to the force of this. So we have to find out the value of current now. So F is IBL, I is going to be force per unit magnetic field and length. We will substitute the values in first case, in second case, in third case, we will get the value of current. That's all. Question number 27 as well. You have to find out force per unit length. We have given magnetic field in x-axis, in y-axis as well as in z-axis, which is 0. Current is given as 10 amperes. Question is what is force per unit length. So what we understood about force per unit length, it is I times P. This is what force per unit length is. So first is force per unit length of the wire if it is in magnetic field that has a component this. Find the force per unit length of the wire if only the field's x component is changed to 0.05. So force per unit length will be represented in all the directions respectively by mentioning in x, in y, in z. So force per unit length in x-axis you'll find out, force per unit length in y-axis you'll find out, similarly in z-axis, and this is the way, this is how you're supposed to have the answers. Did you got this one? For F by L in x-axis, I times Bx you have to do. For F by L in y-axis, you have to do I times By. Similarly for Z, it is going to be 0 because magnetic field in y-axis is 0. Then in second part, they changed x component only. Then in third part, they changed y component only. So you just have to substitute the values and get the answer. That's all you have to do. Similarly, if you talk about question number 26, it is going to be the same. You can simply do it. You can do it very easily. You know the answer, you can simply do it. Question number 27th. It says the wire is bent as shown in the figure, placed in a magnetic field with magnitude 1 Tesla in the indicated direction. The net force on the whole wire, if x is 50 centimeters, it carries a current of 5 amperes in the direction shown. The question is, what is the net force acting on the wire, acting due to wire on the wire? So first of all, let us try to see that how field is going. So field is like that into the plane. So it is going into the plane like that. Current is going this way. So at every point you will observe that field and current, they both are perpendicular to each other. So in which direction force is acting? For the wire, in the horizontal direction, force is acting in downward direction. For wire, sideways, current is going upward, field is acting outward, force will be acting leftward. For this section, current is going downward, field is going upward, current force will be acting in right direction. So the net force will be towards the center, because this is what it is happening here. So what is this net force? This arm will cancel out this arm. So net force is because of this horizontal wire only. For because of the vertical wire, it will be 0. For horizontal wire, it is going to be IBL sine theta. That's all. You have to understand the concept very well, then only you will be able to do it. Did you got this?
Yes, sir.
So I guess whatever number of questions we have discussed questions from those two parts of the unit, like this 2.1 as well as 2.2. We were able to discuss this part, all the questions from this part of your homework part, as well as from this part as well.
Okay.
So third one is left, and I guess we discussed the formula. Most of the questions were formula based only, so you might be able to do it on your own. So make sure you try those out, and if you found any problem, just let me know. We can meet tomorrow as well if you have any doubt for the test. Got it?
Yes, sir.
All right then, let's keep it till here.